Talk will be a bit different from what we have covered so far, and will be more physical robotics and physical human-robot interaction, if you want. So the image of robotics that we have had until 15 years ago, perhaps, was quite different from what we have before. So those big, rigid machines, now we think of robotics more close to humans. Even in industry, we have cooperative robotics. So what has happened in industrial robotics is that we have started, well, there are many things that made the change. But one of the things is that we started looking at compliance, not as a bad thing to fight, to have more accuracy, but rather as a good component of robotic systems. So like in nature, compliance gives robustness, gives performance, velocity, dexterity, and many other good things. So the robots today are lighter, they have more compliance, either active or passive, and this has brought about a big change in industry. Robots with compliance and soft robots are definitely inspired to nature. There is a, throughout nature, throughout evolution, robots, animals and living beings are soft. From the very simplest on the left to the most complex and accomplished on the right. There is an interesting continuums of robots that are inspired more to the invertebrate part of the animal kingdom, where there are beautiful problems. We are also involved in that, but we today will focus on the vertebrate softness, where you substantially take inspiration from animals who also have bones, but still are compliant and efficient. So it will be, for instance, the hand. The hand is not completely soft, but is definitely adaptable and compliant, and it's very complex. Very complex, made of, controlled by many muscles, 19 articulations, 40 muscles, hundreds of thousands of nerve fibers that control the hand. Robot hands used to be rigid. This is a beautiful hand from back in the '84, which could do very refined control of all their joints with a very sophisticated engineering already there. But it would fail even in a simple task as opening a jar, where you see that all the degrees of freedom of the hand are used by the hand. When the hand wraps around the object to be open, but the person is not thinking of where each finger or each joint should be, which is different from the approach that we had in classical hands. What is happening here is that the hand is adapting, is complying with the environment, and the object is taking the shape of the environment. So we started this research some 10 years ago, looking at how we can do hands without overwhelming the controller, either a person or a computer, with the tiny details of grasping. Just like we do, we grasp things without thinking. We basically don't think, we let the hand do. And this is a hologram that a person is trying to catch, and the person, the object is not there. So this shows that really we don't plan for an accurate grasp of the object. We go inside. I can show that again. We overshoot the shape of the object. It's not starting. Well, yeah, okay. We overshoot. Why? Because we are somehow relying on two schemes. One is a template of motion. We move the hand according to templates, geometrical templates, that will drive our hand in patterns that are, in theory, adapt to different objects or different grasps. But then we rely on adaptivity and compliance, so that if we miss the exact position of the environment, we adapt to it and generate the forces that are needed. So these are ideas that brought us to think that it is the environment who really manipulates our hands and not the other way around, as we typically tend to think. So we shape our hands in the environment. From these principles, we derived the design of a soft hand, the so-called PISA IIT soft hand, that has 19 degrees of freedom, but only one actuator, or maybe two, as we will see, that is completely defined in its shape only when an object is grasped, as you see here, or as you see here. So realizing through compliance and through softness some dexterity, but exploiting the environment and living in the environment. Okay, so now coming to prosthetics. Because we started our work in robotics, and then we said, okay, it would be good to have these ideas that come from the human hand applied to the prosthetics. Maybe it's a good idea, because there we also have the same problem. We have a problem of a hand that should be as complex as the human hand, but should be simply controlled, because the interface by which a person controls the hand is extremely simple. First of all, we do not have all the inputs from a prosthetic stump for controlling the many degrees of freedom. And second, it would require too much attention to the person. Even if we had the inputs, it would require too much attention. We don't pay that much attention to our hands. We just go. If we ask a person to do control the independent movements of a hand, he would be burned after 1 hour of use. So commercial devices, as of today, are mostly rigid devices that are inspired to the old robotics ideas. And of course, some research devices have higher degrees of freedom, less dimension and mass, some improvement, but still are not easy to use. Here are some hands that are available today. On the left, you have the simplest one, the cosmetic ones that have no degrees of freedom, no actuation. Then you have the hook. Then you have the 3-digit type that is only one motor and the rigid bone inside. And then you have the most advanced ones on the right. Even the most advanced ones are controlled very simply, and they are still rigid, fragile. They're not very much used still. And of course, there are many very nice research hands, like the ones that I show here, that are not really ready for application because of encumbrance, because of wire. So if you think of doing prosthetics as we wanted to for real people in the real world, we found the difficulty of translating robotics to prosthetics. And we really met with this difficulty, and we thought that, okay, if you want to do this, you have to really put the user and place it at the center of the design. Prosthetics is really a field where you have to do that. I mean, otherwise it makes no sense. Luckily, we have met with people that are in design and also with users that explained us many things about that. So, for instance, one of the important things that not often is considered in prosthetics is the design for social and self-interaction. We use our hands, we use our bodies to do social interaction, like shaking hands, or to touch our own face. We don't think about this, but these are natural things that you do. And you see how clumsy the typical prostheses are in doing that. You cannot really do this. You cannot really use them for that purposes. So the question is, soft robotics help industrial robotics to transition to collaborative robotics. What can it do for prosthetic arms? And how can we translate somehow the advancements in robotic hands to prosthetics? and do some kind of soft prosthetics. So we have made, based on this principle, we've made a development of a hand for prosthesis that is soft. And one of the things, for instance, that we have learned is that the appearance of the hand is an important part to people that wear the hand. And not always it is true that a more human-like appearance, like the artificial hand that we have on the right there, is better received than a clearly declared artificial hand as you have on the left. It's actually because of the well-known, what's this called, the valley thing. It's, yeah, the uncanny valley thing. The one on the right is sometimes felt, you know, like a bit creepy. So many people prefer to have this type of design. The hand allows, because of the softness, allows self and social interaction, takes different shapes depending on different objects, taking the shape of the environment, as I said before. And it's currently being tried in many institutions. So we have currently with Mayo Clinic and Arizona State NIH grant for sending the hand to the house of the patients for 1 month out in the wild, as Adriana was saying, which is something that where you learn a lot. Having a device, a robotic device, for 1 month in a house in the countryside with a patient, and then recording all the data to improve further. The hand was also tried in competition. It's performing well. We didn't win for twice, but we were second. And here is Maria, who is the designer, who is also a user, who contributed to this, some of the ideas on this talk. You see that because of the softness of this process, people, users use it in a rather natural way. You see here Rosa, who was a pilot in this competition. Cybertron is a kind of Formula One Paralympics, let's say. And she is nervously touching her own hand, her own body, like in preparation. And here is Maria that is dancing with another person. Again, these are not prepared. These are candid camera. I mean, it's kind of this. More generally, one could ask, is softness really beneficial to prosthetics? This is a question that, as scientists, we should ask. Because, of course, videos are nice, but so we did try some assessment to see whether, for instance, soft prosthetics was more natural. And we did a hand functional assessment with people, many users, doing activities of daily life, like doing the not only box and blocks, but also tasks like covering a table or doing other things. We tried to measure the embodiment. How much do you feel that that hand is part of your body? How much does it get into your body schema? And the self-location, where is the hand? I mean, you don't see the hand, where is the hand? That kind of question you ask. The sense of agency, what can I do? Can I do with this or can I not do with this? The body ownership. A very interesting experience we made with a person that was bilaterally amputated, actually for even the legs. And this person really enjoyed the hands a lot. As you can see the difference between the compensation that he needs to do with conventional commercial hands on the right and soft hands because of the adaptivity to the environment. And when a person has a bilateral amputation, you really gauge the role of prosthesis because with only one hand, people tend to neglect the prosthetic hands and use the other hand. But when you have a bilateral amputation, they really, it's really a game changer. Ironically, this person is not using active prosthesis in his normal life, but he was happy with the soft prosthesis. Here is a picture of this person. Here are some quantitative tests showing that indeed there are advantages. And so we're moving a little bit further, asking now, this idea of softness, can it be extended to the rest of the prosthesis? Because the hand is part of the prosthesis, then we have the wrist, we have the elbow, maybe the shoulder in some cases. Again, this is the situation that we have now with some very nice engineering devices, but mostly rigid. And the question is, would a soft or compliant arm, or an arm where you can change the compliance at will, would that be useful or not? That's not an obvious question. With comparison to a rigid robot. It's not obvious. So for instance, Jan Sensinger in 2008 studied this problem and found experimentally that a person moving an arm and being able to change the stiffness, so the arm could be, this is a virtual arm, it's a virtual prosthesis, it's not a real prosthesis. But the person was able to change the stiffness. So it could use the stiffness, very low stiffness, or very high stiffness, or switching between the two. And he tried some tasks where the advantage was not there. So people performed better with a stiff arm, which makes sense in some cases. Because if you have compliance, then accuracy of movements, for instance, is worse. On the other hand, there was paper by Blanco, Kamura, Whitcomb, and Neville Logan, of course, before, that instead, in other tasks, found that there was an advantage in having compliance. For instance, in minimizing the force at impacts. Imagine of receiving an impact on your hand. If you have compliance, then you can minimize this. And if you're walking, and you hit something, having compliance is good. Can be good. So together with Sensinger, Okamura, and Hogan, we started a protocol for trying to understand, is it good or is it not good, and how it can be. So we started with this virtual prosthesis idea, trying to do tasks such as reaching and holding in the presence of a perturbation. I reach a position and then I try to hold it, although I have a perturbation that moves my prosthesis, or track a trajectory, again with perturbations, or minimize contact force when you have something that acts from outside. So of course these are different tasks that require different things. And eventually, it's not unexpectedly, we found that for accuracy tasks, rigid hands are better. For tasks that imply minimization of contact forces, softness is best. Variable compliance, that is a prosthesis that can be either soft or stiff on command from the user, is never best in any single task, but in the compound index, it is the best option for patients. So these are the numbers. So we started designing new, and we are going now towards new directions. With the hand, we are now developed a pediatric version that we can use with little children during their growth. We have a multi-synergistic prosthetic hand that will allow people to move the fingertips independently. We are studying and seeing to implement palmar arches, like in our hand we have palmar arches to have a better grasp. And especially now that we have some idea that variable stiffness in prosthesis is good, we are building a complete new arm, elbow, wrist, and hand. There are also developments that show that the idea of softness is good for prosthetics, even in feet design. As you can see, a characteristic that people don't think very often is that all robots and all prostheses have flat feet, which is completely different from what humans have. So there must be a reason why we do not have flat feet. And but robots all have flat feet. And most prostheses have a flexible carbon sole that is not adapting to objects. So we are now studying. You see, for instance, that even the HRP4 just it fails on a very tiny object under the foot, you see there. But when you add our version of the soft foot that you see on the right side there, it adapts much better and negotiates object without changing the controller. So this is another direction of research. The VSA arm that I was mentioning before is using an antagonistic approach to the design of the arm so that you can change stiffness, as you see in these two videos. There is a wrist. The wrist is a complicated mechanism. It has 3 degrees of freedom that you have to do. And the human wrist is very important to manipulation. It's not easy to replicate, and especially if you want to add stiffness. So it was very difficult to have 3 degrees of freedom with independent stiffness, so we came for a solution that has only 1 stiffness for the whole wrist. So the wrist can be either soft or stiff in all directions at the same time. And here is the final new prototype that unfortunately I'm only able to show in a preliminary video because the work is going on here. So this is the new soft arm, wrist, and hand that we have been developed. We didn't start doing experiments with patients now. Now, one, I'm doing okay, I think. One final consideration that I'd like to make is that when you increase the number of the degrees of freedom in a prosthesis, we don't need this. Then, as I mentioned briefly, you also have to control them. The person has to control them. Now, if you take this arm, you have an elbow, which is 1 degree of freedom. But if you have variable stiffness, it's 2, because you can make it softer or stiffer. And then you have 3 in the wrist plus a stiffness. So it's 4, 6. And then we have in the hand, you can have either 1 with the first version or 2 with the second version of the hand. You have 2 more. Now, today, the interface that people, normal, commercial interfaces to interfaces only have 1 channel. It's typically 2 EMG channels that measure agonistic and antagonistic. You can at most extract 2 inputs, 1 for the position and 1 for the stiffness. How do you go about the rest? How do you control the degrees of freedom that we really need in arm? So there is this balance. In some sense, we're trying to make it as simple as possible, like in the hand. But on the other hand, you would like to have some new features. So here is reported some work that we are doing with Dario Farina at the Imperial College and Oskar Assmann in Vienna that looks at high-resolution EMG sensors on the stump of the person. And tries to reconstruct the spiking neuron signals that come from the spine to the muscles. So from those signals, we are trying and we are able to extract more information than from the surface envelope EMGs that are conventionally used in prosthetics. So on the right here, you have first videos of a person that is using a 2 degrees of freedom hand with only 2 muscles involved and controlling the fine motions of the hand, including inner in-hand manipulation for like tilting a glass or doing some fine manipulation. Okay, I think I have 5 more minutes. Just to mention another application, I will be very quick here, in rehab. So we are not talking about prosthesis now, but there are pathologies that are very important, like a stroke, where the person is affected by spasticity. When you have a stroke, the real damage is in the brain, but the muscles in the hand and the arm get to a contracted situation, often get to a contraction. And the people are not able to use the hand, as if the muscles were damaged. And much of the rehabilitation is trying to relax the muscles and doing exercise on the muscles, not realizing that the real problem is not in the muscles or tendons. The real problem is in the brain. So a tendency in neurorehabilitation is to allow plasticity of the brain to recover the control of the hands. So the idea that we were trying to pursue is to see, well, what happens if my control of my hand is impaired? So I have now a spastic hand. And if I try to move the hand, I'm probably still able to send some signals, but they will not make it throughout the hand. They will be very weak. This is what is observed. What if we use a hand that is not the real hand, but is another hand that looks exactly like the hand, and that moves, like your hand would move? So you see here the picture of the spastic hand, which is close to the artificial hand, and that the signals of the control signals from the person, the patient, are devoted to controlling the robot hand. So we did a first pilot. You see the protocol here. The patient is wearing a third hand, a supernumerary hand, an extra thesis if you want, and a person, the therapist, is helping the person with the weight of the arm and for safety, and the person tries to control his hand, but he sees the effects of his efforts on an effective hand. That is a prosthetic, looks like his own or her own, which is concealed to the view of the person. So that was, here are the experiments. You see, so it was interesting to observe that people were really involved, really even emotional about seeing the hand work again, especially when you conceal the real spastic hands. And in at least the pilot patients, we have observed a good, well, at least we proved that there are no counter effects. It's a safe procedure. Spasticity is not increased. And now we are going for a larger multi-center study with 4 hospitals involved to see whether in the larger numbers we can really affirm that this is as positive for therapy as we hope from the pilot study to be. So this is the work of many people, of course, that I thank together with you, and I will leave you with this use of the soft hand in a playful application. Thank you very much.
Thank you, Antonio, for a very great talk, and it's time for questions. Okay, who wants to start first? Who's brave enough? Okay.
Thank you very much for this very nice talk. Yes, one question. What about the way that the patient controls his own hands? What about this interface?
Yeah, so as I say, we are, for the hand, the 1 degree of freedom hand, we are using 2 EMG, like conventional Autobach EMG channels, envelope. I don't know if you are, if you know the field a little bit. So the classical interface that we are using, that people are using since 50 years or 60 years. Right? So we are using that. Then, as a research, we are investigating different controls, and I mentioned 2 paradigms. One I showed already. One is we try to extract from high-density EMGs more information, like Professor Farina, Dario Farina's style, is going back to the spiking neuron signals and then trying to find more information about the controls. We have demonstrated the control of 2 degrees of freedom instead of 1 so far, so it's still a long way. Another very interesting thing that I mentioned is the use of compensatory motion from the user, which is a technique that comes from here, from Paris, basically. It's a group in ISIR. The PI is Nathanael Ijaras, and a student was Mathilde Legrand, that came proposed a very simple, interesting idea of looking at the compensation movement of the patient to infer the intention and then control the prosthesis. So they basically, if you have imagine that you have a wooden prosthesis, right, fixed. Then you want to reach here. Then what you do, you move your body, right? And the idea is that if you move your body towards there, then you are in a less comfortable position. I can use this error with respect to my rest position to feed back in the control of the hand. So my hand, which is really active, will get elongated, and I can relax. So this idea, I thought it was very nice. I'm happy to make some publicity to the group. And we are picking over from there. We are trying to make this valid for different configurations. So this is a possible avenue to enlarge. The problem of controlling prosthesis is important. The question is quite on the point. We can build prostheses that have 25 degrees of freedom. Nobody will ever use them. Yes. There is one on the back, on your back.
Oh, yeah, okay.
Okay, thank you. Very impressive speech. I found very interesting about the third hand of the people, and I think it's like a sensory remote learning from adult to learn how to build a connection between the perception and the motion. My question is about, can we like use a virtual reality device like a VR glass to training the people in a virtual world, and we can guide maybe the patient or the people to use the second hand or even the fourth hand in a very designed world. It will be better than the reality world to training the people. Thank you.
Yes, of course you can imagine of doing a similar experiment with a virtual hand. And I think this has been done. It's sort of a glorification of the rubber hand, or the mirror therapy. We have found that the fact that you grasp a real glass and you drink from the real glass makes a huge difference in the sensations that you have. And as you said correctly, it's really a sensory motor retraining. And indeed, one aspect that I didn't mention is that if you also bring back feedback from the hand to the patient, that also increases the effectiveness. So yes, you could do that in virtual reality. In our experience, it's not quite the same thing.
Okay, thank you.
Yeah, hi. Thank you for the talk. I especially like the expressivity that you can reach with the soft hand. And I have two questions. One is rather detailed. I'm curious, how far is the development? So is the variable stiffness fixed, or is that something that is personalized to the user's anthropometrics, especially in the case of, let's say, athletes that could have overdeveloped one hand and the other one is less developed, let's say, in terms of muscle strength? So that's one question. And the other question, if there's any attempts in developing material recognition of the soft prosthesis. I mean, of course, the user is still seeing unless they're blind.
Material recognition?
Yeah, type of the material. So if
the type of the material that you are touching.
Yeah,
okay.
Or temperature or anything like that. Yeah.
Okay.
Thank you.
Okay, I can answer the second question first. Yes, recognizing different objects or different shapes or different textures, that is a classical benchmark for prosthesis. If I mentioned quickly the Cybathlon, which is a competition between different prostheses used by different pilots, ACA users. One of the tasks of the Cybathlon is to put a hand in a box, in a black box, and recognize which objects are there from the texture, for instance. So the material, the compliance, or the texture of those characteristics. So yes, in real life, vision does a lot. So in most cases, we have found with patients that it's not worthwhile to add too much technology, because if they touch things, they see the corresponding behavior. And vision is a sense that captures all in our sensory motor system. So we believe our vision. But if you are doing something with a hand that you don't see, then definitely it is important to have feedback, sensory feedback. I didn't touch on this. We do have research on bringing information back on the stump. We also have patents and some devices. First question is the customization of the variable stiffness. No, we are not there yet. Actually, we would be happy if we had one working model anytime soon. Even more than that, I mean, we are still now concentrated very much on understanding whether it's a good idea or not, because having variable compliance, controllable compliance, means adding technology, which means cost, weight, inputs. So in this, if you want to really be, if you are concerned about patient and usability, then everything you add should be carefully considered, not to do. Not if writing papers is not your only goal, then you better pay attention.
Okay.
Short question. Thank you for the talk, Antonio. I have a question. It seems to me it's hard to have a multidimensional input signal into the arm, so what the user can control, so you had 1 or 2 dimensions at the moment. But from your last answer, I assume that it's easier to provide feedback back with some devices on the skin. So wouldn't that be an option that you use the feedback from the hand in order to select the dimension you want to control? So although you can only control 2 dimensions simultaneously, you could actually switch the dimensions of the control based on feedback that the arm gives you. In this way, you have only 2 dimensions at the same point in time, but you can actually switch the dimensions. And that would give you maybe 4 dimensions you could control.
Okay, if I understand correctly, so first answer in 2 parts. So first part, easy. What people are doing with advanced hands today is you have a hand that has, for instance, 5 independent fingers, but you have only 1 input, right? 2 muscles that act agonistic, antagonistic. So how do you control the 5 fingers? They pre-program behaviors like pinch grasp or power grasp or maybe another, and then they control this mode, or they switch mode and they control another mode. Switching can be made explicit by persons, by the patients. So for instance, in some cases they do a series of co-contractions. I co-contract 3 times. It's like a Morse alphabet of co-contractions. And then I switch to pinch. And then if I do it twice, then I move to power. And this is okay, but after a few hours of use, people get fed and don't use it anymore. And many people I met, many users I met, have a fancy $40,000-$50,000 hand on their desk and use a very simple hook or even cosmetic hand because they don't want to pay attention to what they are doing every time. Even some others are, they have a phone interface and they program the grasp on the phone and then do the grasp, which is kind of terrible, of course. It's not really welcome. But if I understand correctly, your question is subtler than this. The question is, could I switch autonomously between the modes based on the feedback? And that is a new point. I don't have an, yes, in principle you can. It's a good idea. It goes a little bit towards the autonomous prosthesis, which is something that I didn't touch. But one possibility is that you put autonomy, you really have a little robot, which is, partly already there because the hand is taking shapes that you are not controlling. So the hand is already doing something that is beyond your explicit will, right? So in your there are studies, for instance, of people who put a camera in the hand. And depending on the object that the hand sees, the hand autonomously takes the shape suitable for that object. Okay? So these are, of course, this is possible. Again, I think the speeches that were before me already explained well the possible different acceptances that we could have from different people, right? Would you like to have a hand that whenever sees a glass grasps it, or maybe not? Or maybe it should ask you. autonomy and prosthesis is an interesting thing. But I'm not against that, I must say. And indeed, having some form of avatar prosthesis, it's you, but it's not you in the tiniest details, right? As far as as far as the robot hand understands what you want, that should be fine. So I think there is a lot of ground to be covered there for this kind of investigation.
Okay. I don't know. We have time for like one short question, maybe. No.
Let's have one.
Yes. Okay. Let's do it.
Thank you for your speech. It's quite enthusiastic. At the end, you mentioned therapy. So you moved from prosthesis to therapies. Or are you working with neurocognitive or psychologist, or just to understand the switch in therapy, what it implies?
Yeah, I'm working with neurorehabilitators, neurorehabilitation hospitals. Person in Genova is Professor Trompetto. Person in Pisa, Chisari. I don't know if you know any of these names. Yes, these are neurorehabilitators, basically people who treat subacute patients after stroke and even some other pathologies. And it's the same, typically in Italy at least, it's the same department, which is rehabilitation. Prosthetics is considered part of rehabilitation. But these are different specializations. Yeah, and the suggestion came actually to go in that direction came in part from one of them. So it was very nice to talk with his medical doctors and get this idea. Thank you.
Let's thank Antonio again for the great talk.
Thank you.